Welcome to part 2 of the lecture on prototypical equations. So what I'm showing right now is the Navier-Stokes equation. This is the same one as I showed in the introductory lecture. And I would like to rehearse the three things that I pointed out in that lecture as well, those three difficulties. So the first one was that we have this combination of a pressure field and a velocity field. That had to do with the mixed nature of the problem. The second difficulty was that we have this term that we're unfamiliar with. That is an advective term. And the last difficulty is kind of rooted inside of this advective term. That is that this is not just any advective term, this is a non-linear advective term. So we have this non-linearity rooted in there. Now the remaining terms I'm not highlighting, and this is for a reason. Those are typically not the terms that we struggle with. In fact, these are the same terms as you might find in other equations for which we have no issue whatsoever. So we have a time derivative. Well, this is something that we can typically handle without too much difficulty. We have here this diffusion equation. Finite elements can handle diffusion type problems extremely well. And then we have this right-hand side forcings. Well, forcings are also not typically any issue. So it's really these three things that make this equation so difficult to handle. And we're going to now obtain three equations that represent these three difficulties. And the one that I'll start with is this advective term. So I'm going to try to define an equation that is almost exclusively based on this advective term. And the equation that I will derive is the advection-diffusion equation. And the advection-diffusion equation is of relevance if we have a defined flow field. So the flow field itself is set. For instance, the wind at any particular time, subsurface flow, or maybe the blood flow in your body. So that is defined. And we're interested in how a certain chemical or constituent is transported by that velocity field. So taking the same examples, we might be interested in biomechanics, in the way that medicine or drugs are distributed in certain organs. So we would have the medicine as a constituent that is transported by the blood and is also diffused. So we have this advection-diffusion. We might be interested to find out if we sneeze, how are the droplets, how they are dispersed into the open air. So these droplets are again advected by the flow field and they diffuse. So it's an advection-diffusion. And for a bit more civil engineering oriented applications, subsurface flow, we might have some contaminant somewhere. We're interested to find out how it's distributed beneath the surface of the earth. So you would again have advection and diffusion. So in general, this is a transport and diffusion and I haven't pointed out heat, but heat is also a very typical example of heat or some chemical due to an advective field. So the point being that we have a set velocity field. So I'm drawing here some arbitrary combination of velocity lines. And some chemical or heat is transported and at the same time diffused. So we're going to represent our temperature or our heat concentration or our chemical concentration as with the symbol phi. And then these lines represent the velocity for which we'll use u. So we have phi as a concentration. This is a scalar quantity. We have u as a set velocity field. This is a vector valued field. Now, when we were talking about the different reference frame that we might use for our mathematical description of the physics, we talked about Eulerian and Lagrangian. And we said that for the Lagrangian framework, we track materials, so we could actually write out Newton's laws on these material points, or these material elements, or whatever. And for the Eulerian perspective, we have to look at control volumes, and we're trying to find a balance of something that flows in of that control volume and flows out, and there's a balance between those. So the balance law that we might set up for this advection-diffusion has to, we first have to define a control volume. So let me draw some arbitrary shape here. That's going to be my control volume. This has a normal vector on each side. So this is the unit normal vector. Of our control volume. So what is going to balance here? Well, we have this concentration field phi. We find that this flows into some parts of the surface of our control volume. It flows out on other parts. It may also be generated, right? If we have some chemical reaction, then phi might get generated, might get created. So those are pretty much the different ways in which the amount of our concentration phi in our control volume may change. And that is precisely the balance law that we're going to write. So we have a balance law. Now we're going to say if we integrate the quantity phi on this domain omega, so my control volume here is omega, then the time derivative of this total amount is going to have to change based on what is going on the boundary of omega, denoted by partial omega, plus some volumetric source term. So this is going to be the source. That is whatever is generated from within the volume itself. So now what's going on in the boundary? Well, we have this advective field that is transporting phi inside of our domain. So that's going to be one term in our equation here. So how would we write this? Well, the amount of phi that is transported across any point along the surface is going to be, well, phi that is on that surface multiplied by the velocity u, but only the part of the velocity that is normal to the surface. So we have u dot n. And of course, because these signs are opposite, we're going to have to introduce a negative sign. So we get minus u dot n times phi. So this is our advective transport, which is the advection. Now the equation is called the advection-diffusion equation, so we're going to have to introduce something else as well, a diffusion part. It is dependent on the physics whether or not this is a relative part, if this is a concentration that tends to diffuse then we need to add this. If this is a relatively inert type of concentration that does not diffuse, then we might be happy already. But we're going to go for something that also diffuses. And what kind of relationship do we have when it comes to diffusion? So suppose that we have certain concentration along any line here. So I'll take a look along this line. And suppose that at some point phi is going to look like something like this. So we have very little on the right and we have a lot on the left. Well, naturally diffusion, what that means is that the concentration where it's high is going to move slowly towards where it's low. So that means that phi is going to move in this direction. And the steady state of diffusion is that something is constant. So we have this homogeneous spread. So in terms of transport at any particular time, we find that this is related to the gradient of our concentration. At points where the gradient is 0, there's not going to be any transport. What that means is that in terms of a random walk, any concentration that slightly moves to the left is balanced by any concentration that is diffusing to the right. So we have a net change of 0. Whereas at places where we have this high gradient, then statistically at the places of the increasing gradient, there it's more likely that the concentration moves to a place with towards the direction where the gradient is, where the concentration is decreasing. So in this sense, we can write the rate at which we have this diffusion to be proportional to the gradient of phi, and specifically negative the gradient of phi, right? Because it's moving in the opposite direction of the gradient. And then also multiplied by some material constant. So let's go with mu here. So this is our diffusion coefficient. So that's another term that we're going to have to add here. So we have another boundary term, because this is again whatever is diffused into our domain. That's going to happen according to mu gradient phi dot n. And I've lost my, my negative sign here because again we have the normal pointing outwards. So these are both surface integrals. You know what? Let me combine those. I'm going to have to shift some stuff around, but that's fine. So we have one integral across the boundary of our control volume. We have this contribution in negative, this contribution in positive, times ds is a surface integral. And this is our diffusive contribution. So this relation that the transport is proportional in magnitude and direction to the gradient of the concentration for concentrations, that is called Fick's law of diffusion. For heat, it's called Fourier's law of diffusion. So they occur in different physical phenomena. Okay, so now we have an equation that relates things that happen on inside of the volume, one way on the left, another way on the right, and some things that happen on the surface. Now, to make a partial differential equation of this, we want to have everything happen inside of the volume. And the tool that we have for this, to rewrite surface integrals into volume integrals, that's going to be the divergence theorem. So that's going to be something that shows up a couple of times. And the divergence theorem says the following. The integral on the boundary of any arbitrary domain of some vector valued function f. Well, let me go with g, because I'm already using f. Of g, dotted by the normal, that is going to be equal to the integral inside of the volume of the divergence of g. And here we have a ds, and here we have a d omega. Now Let me specify here some of the differential operators that I'm using, just to make sure that we're clear on this. So I'm using here this gradient. Sometimes it doesn't want to change color. I still have not figured out why that would be the case. No, do it like that. So here we see a gradient operator. And here we see a divergence operator. So let me explicitly state what these are. So the gradient operator acts on a scalar valued function. So in our case here phi. And it produces a vector. And it produces a vector of partial differential operators in this manner, depending on the dimensionality of our physics. This could be 1, 2, 3-dimensional. Now the divergence operator actually acts on a vector valued function. We have the divergence in this case of g. G was a vector valued function. And this is going to produce a scalar, and the scalar that it produces is again dependent on these partial differentials of the different components of our vector. And it's going to be the sum of these different components and their partials in the different spatial directions. Ah, come on. A little stuck now, etc. So this is notation that I'll actually use repeatedly, and I hope that this is something that you're familiar with. Okay, so how do we make use of this divergence theorem in the balance law that we wrote up here? Well, we find that we have this surface integral here, and we have a surface integral of something that is dotted with this normal, right? So we have a normal here, we have a dot normal here. Now this was a scalar quantity, but the thing that we're dotting with here is a vector quantity. So we're able to do something that looks like the divergence theorem. So let me explicitly state that here. So we had originally an integral along the boundary of our control volume, and I'm going to collect everything into a single object that is dotted with the normal, and that will be minus phi u plus mu gradient phi. And this was dotted with the normal, so that's going to be effectively our g in this divergence theorem. So this I can replace by an integral over the volume of the divergence of this quantity. Yeah? So this is going to be identical to an integral over the volume of omega of the divergence of minus phi u plus mu gradient phi. Now does this make sense? Are these all vector valued functions? Yes, we have u, that's a vector, multiplied by a scalar, that's still a vector. And mu, that's the gradient of phi, well the gradient of phi, that was a vector. Yeah, so this makes sense, to operate a divergence on a vector valued function here. So what does our balance law look like right now? Well, if I move everything dependent on u to the left hand side, then I would say an integral over omega of, and we're allowed to pull this time derivative into the integration, right? The integration differentiation can be swapped in terms of order. Then I'm moving this term to the left hand side, then I'm applying the divergence theorem. You would get the integral over omega of the time derivative plus now this new term, or minus this new term. So I'm going to put the minus inside of the brackets. That gives me plus the divergence of I think I'll separate this. We have the divergence of, phi u minus the divergence of mu gradient phi. And that's going to be equal to still this source term that we had on the right hand side as simply f. So I'm not very used to writing the dS's and the d omega s, as you can see. I hope that's clear. Okay, so now this is a balance law that is talking about the balance of our concentration field phi on some control volume, but I haven't really specified the control volume. This would hold for any control volume. This would hold for a rectangular control volume, a circular control volume, a large control volume, a small control volume. In fact, this holds for any arbitrary small, large volume, and since this is the case, this has to hold pointwise. Yeah, so even this is a volumetric integral, is because our choice of omega is arbitrary. The only way that this is going to hold for any possible choice of omega is if this holds in a pointwise sense. Meaning that we have the following partial differential equation. And this is the advection-diffusion equation. I'm still not allowed to use a red pen for some reason. So this is what we typically call the transient advection-diffusion equation. Transient means that it's not steady state, and that we can see because of the time derivative on the left hand side. So I want to simplify this equation because I want to get to the core of the advective problem. So I'm going to make a couple of assumptions. So suppose that we make the assumption that first of all we're in steady state. That means that the time derivative is 0. Secondly, I'm going to assume that the coefficient mu, which is the diffusion coefficient, is spatially constant. That's going to mean that minus the divergence of mu times the gradient of phi. I can pull out this mu because there's no spatial derivatives here. So it's going to be equal to minus the divergence of the gradient of phi. And by shorthand notation, we actually typically write this as minus mu times the Laplace operator. So this is completely equivalent. These are definitions. And as a last assumption, what I'm gonna state is that the divergence of u is equal to 0. Now, how does that affect my equation? That means that the divergence of phi u is going to be equal to u dot the divergence, sorry, not the divergence, the gradient of phi. Yeah? You can only use a dot operator if both sides are equated. So you can test this out yourself by using index notation, but this is will become an identity when the divergence of u is equal to 0. Now, what does that mean? A divergence of u being equal to 0. Let me actually spend some additional words on that. So this is called a solenoidal or divergence-free vector field. Solenoidal is synonym to divergence-free. Divergence-free is very clear, right? The divergence is equal to 0. Solenoidal is a difficult word for the same thing. Yeah, so whenever you see a solenoidal vector field, then it just means that it's divergence-free. Now, what does it mean for a vector field to be divergence-free? Well, this is actually one of the conditions that we're also seeing in the Navier-Stokes equation. This was our second line in the Navier-Stokes equations. And we'll see in a bit where that comes from, but I can already spoil the result for you. This means that the vector field is incompressible. That means that the material does not increase its density, right? So this is incompressible flow. And I'll get back to that once we derive the Navier-Stokes equations. So this is not a very strange assumption. Many applications involve incompressible flow. In fact, really the only reason why you might want to consider compressible flow is if you're talking about airflow that is at such high speeds, high Mach numbers, that it starts to compress and it produces shock waves. But in most engineering applications that might be of interest to you and me, specifically for civil engineering applications, we're interested in incompressible flow. So if I now make use of these three assumptions, then I can simplify the transient advection-diffusion equation into the following statement. What I would get is u dotted with the gradient of phi minus mu times the Laplace operator acting on phi is equal to f. And this is the form that I will typically use when I'm talking about the advection-diffusion equations. So I have no idea why I'm now suddenly allowed to switch my pens again. I'm still figuring this out a little bit. Okay, so this is our first prototypical equation. How do we get now to this conclusion? Well, the term that is of interest here is, again, it's not the diffusion part, because that is something that finite element methods can handle really well. It's this new term. It's this funny unsymmetric term. That's also the same term as we could see in the Navier-Stokes equation, where we have this advective field dotted with the gradient of our solution field. So that is an advective term. And that is the term that is of importance in this equation here. So that's the term that we'll study when we study these equations. Now, to kind of motivate or show you that this is indeed a problematic term, I have here a small example. So I have here an example of an advection-diffusion equation, and there are different combinations of how much the advection dominates and how much the diffusion dominates. Right? So I have my advective field here as A with a set value, 1.8. I'll use 1.8 consistently here. And the diffusion I'm going to decrease. So I'm going to change the balance between the advection and the diffusion. So in this model problem, I consider a rectangle or a square domain with the hole cut in the middle, and I have certain boundary conditions along all the edges. Around this circle, my concentration is set to 0, or if you prefer, you can think of a temperature as well. So the temperature will be set to 0, and around the boundary of this square, I have it set to x plus y, so we get this linearly varying temperature. And we find that if we solve this on, well, a given course, a given mesh, then if I have a high diffusion, then things work quite well. I get a smooth solution field, and this actually looks quite a bit like what it's supposed to do. In case I would keep on refining, I would not see a significant change in the way that this solution field looks like. Now, if I start to decrease my diffusion, then I see that these layers, they become steeper and steeper, and this produces certain undershoots here. So we get already sort of oscillations. And the finite element method is no longer able to handle these sharp gradients, and as a result it is an undershoot and probably here actually also a little bit of an overshoot until it sort of stabilizes. Now I can extremify this. If I go yet one factor of 10 lower with my diffusion, then I get a result like this. Well, this looks very clearly quite horrible. In particular, the thing that is important here are the values below 1 and above 0. The advection-diffusion equations typically involve concentrations, right? That's the field that we're interested in. A concentration of below 0 and higher than 1 would be unphysical. So these kind of oscillations can really mess up the physics in your simulation. Now, and I can even go further than that. If I decrease by yet another factor of 10, then I can't even show you this in 3D anymore because the spikes are so large. And now I can show you is that you have huge oscillations, and it's by no means able to represent the true solution of the advection-diffusion equation for a case like that. And that is what I'm talking about when I'm talking about the advective instability. So this is not a problem due to the diffusion. Actually, the diffusion stabilizes the finite element method, and only once we start to decrease our diffusion and the advection becomes dominant, and then we see this unstable behavior. And that's why this is one of the prototypical equations, one of the clear examples of what the finite element method struggles with for fluid mechanics applications, and that is that advective term. Okay, thank you for your attention.